you missed, or anybody who missed or whatever, they can go to the YouTube website and review your notes. Okay, welcome back to Organic Chemistry, Introduction to Organic Chemistry 2330. We're here on a nice Tuesday morning. It's quite cold over at my place, so nice and fall, spring feeling though. And so what we're going to do today is we're going to continue on with our chapter that we're going to be reviewing. This particular one is going to be chapter 4. But let me go ahead and answer a few questions about tomorrow's lab first. Okay, make sure you go and find out if you are in sections 2, 5, 1, or 2. Those are the live sections. You need to go onto campus and meet at lab chemistry 229, okay? If you're in either lab section 301 or 302, then that is a completely online, and you have a live Zoom session during that class time. So, that will be for you to meet your lab instructor to give the pre-lab lecture, and then they will give you instructions on how to take the quiz on Canvas, okay? So we'll be doing that, as you'll be doing all of that tomorrow. Okay. So I did send out an email and had a couple questions about that. And so I've answered some questions there, but I think everything else will be revealed by your lab instructors tomorrow. Okay. All right. Any questions about the lab real quick?
I have a quick question.
Yes.
On my schedule, it says I'm in section 301.
Yes.
But on Canvas, I have a tab that says section 252.
Okay, that's weird. What is your schedule says 301?
Yes.
Okay. But that, yeah, all of the labs are going to show up on the Canvas site. So let me see. Let me look up your name real quick.
Mine actually says the same thing, and I'm in an online lab too.
Mine says the same thing. I signed up for the in-person lab, section 251, but then I go to my Canvas page and it says 2130.
Yeah, 2130 is it should be section. Okay, I have all of them divided up by different numbers at the end. So on your section, if you look at that should say Chem 2130-301, 30 something or 25 something. The 25 something is the live. So but under assignments, they're just all by the different labs. So, okay. I don't understand why there shouldn't be any groups under the people tab. There are no
My question is, say if I miss, like if I'm supposed to be online and then it turns out for some reason I was put on an in-person class, will that be a missed lab for me? Because I don't want to miss a lab just because there's confusion.
No, you are allowed. This is actually a good point, because if you end up, if you are in live lab and you end up getting exposed or having a positive COVID test, you have to join the online class for the recommended amount of time, which is 2 weeks. So at any point in time, if you, are in the live class and miss one, you actually get to make it up on the online portion, okay? And so the online portion will be a component where you have your quiz on Canvas, you have your pre-lab and post-lab you upload to Canvas, and you actually have your pre-lab lecture live with your lab instructor, and we will record it, and so that you can actually review it later. And then the lab actually shows up on the actual lab procedure that you write down data with will tell you that. If we're online, do you need the lab notebook? Yes, you need the lab notebook even if you're online, because after your pre-lab lecture on YouTube, you'll watch the lab. And the lab is just laid out where you actually see everything done and you make observations as you go through the lab. You record all those observations down in your lab notebook, and that ends up being your lab data. Those also have your pre-lab questions and your post-lab questions. So the lab book is necessary, for the online portion as well. And you have to turn in everything by midnight on Wednesday night. Okay. Has anyone on the online lab been able to find those Zoom links? Those have not been posted yet. Those should be posted today or tomorrow. So there should be a tab here in the announcements. There'll be Zoom link for the 2 different online sections. The one is at the 12:30 and one is at the 3:30. Wednesday, the same day. So the quiz, the pre-lab, the post-lab are all due on that day you have the lab. Okay. And so especially most of the time you do not use the whole lab time, only a couple of labs you do in live. And the rest of the time you can devote to getting that pre-lab, post-lab, and the quiz done and uploaded. And they can be uploaded as PDFs or images. We can grade both. Okay. All right. I will also send out an email tomorrow morning with some additional information about those, so that look for that email for tomorrow morning. Okay. So does that cover all the questions about the lab? Once we go once, I think you'll see it's pretty easy. You just want to make sure you look at Canvas for the due dates to make sure that you're on the right lab that week and that you're getting those things uploaded. And yes, you can turn things in late. If you're sick, they are counted as late, just go ahead and put them in. And if you just ended up not getting it in, you can turn it in for a slight point deduction. So I am accepting late assignments, no more than a week late, please. Okay. All right. So what I'm going to do is I'm going to go ahead and share my screen. We're going to go back to, let me go ahead and put that up. If you really can't tell which section you're on, go ahead and email me. I have a list here of what are it should be on your official schedule as to what section you're on now. But I have it on mine where I think everybody should be. Okay, so I have right here, you should see my chapter 4, Alkenes and Alkynes. Okay, is that good? Yeah, see that? Okay, so last chapter, we talked about alkanes. Okay, so alkanes are hydrocarbons that only have carbon and hydrogen bonds, and they only have single bonds. Okay, and we saw they really didn't do very much because the carbon-hydrogen bond is not very polar, and therefore it has very low reactivity. And the only thing we really ended up doing with it was burning it. Okay, so now we're going to introduce that double bond into the system, that pi bond. That pi bond actually has a lot of different reactivities that those sigma bonds don't have. And so I want to differentiate those by talking about alkenes and alkynes. Okay, so the alkenes are the ones with a double bond, and the alkynes are the one with the triple bond. Okay, so this extends what we saw on hydrocarbons. A saturated hydrocarbon is one that we couldn't get any more hydrogens on. However, an unsaturated hydrocarbons means we could add a hydrogen across a double bond or a triple bond. That's why they are unsaturated, okay? And they can even be unsaturated as things that are benzene rings, but we'll get into that in chapter 9. Let's just talk about alkenes and alkynes. So the general structure of alkenes or alkynes is based on the balance between carbon and hydrogen, okay? So for every one carbon, you get 2 times that hydrogens, okay? So if we had 6 carbons, we would have a total of 2 times 6, 12 hydrogens in a simple alkene, okay? So that is just where you have a single double bond somewhere in your hydrocarbon, okay? The alkyne, because you take 2 more hydrogens away to get to that third bond, to get to that triple bond, it's actually going to be that 2n minus 2. Remember, the saturated is 2n plus 2. So that's where that you add those, you can add 2 hydrogens across here to give you your saturated hydrocarbon. So those are the general formulas for alkenes and alkynes. Oh, I have to admit. There we go. Okay. So the other kind here, and again, we'll focus on it more in chapter 9, is what we call arenes. And so that's when you have alternating single and double bonds in a ring. That gives them very special properties, and we'll have they have a bunch of different reactivities that we are going to talk about when we get there. But this is the benzene ring, or an arene system, and it's another classification of the unsaturated hydrocarbons. Okay, so while we're not going to study that, we need to realize that this structure kind of shows up as a substituent on a lot of things. And so the reactions we're going to talk about in the next few chapters do not work on benzene rings. That's why we separate it out into a completely different thing. But we need to have the concept that a benzene ring, which is just 6 carbons with alternating single and double bonds. So really it's an alkene, but it doesn't react like an alkene. That's why we separate it out. The other way to draw it is if it's a substituent on a chain, we can draw it like this. We can also do C6H5 dash. That's telling us one of those hydrogens were removed, and we can capture that. The other way we do it is we actually are lazy and put a pH for phenyl group. Okay. So these are the different things. You might see them hanging off something as a benzene or one of these rings or this pH. It's just a phenyl group, and they do not react the same way the alkenes and alkynes do. So, but even though it looks like it. Okay, so let's talk about alkenes in particular. The first and most important thing about alkenes is this bond is sp2 hybridized, and the P, the unhybridized P, is the one that makes the pi bond. So if this carbon is sp2 hybridized, that makes it trigonal planar, which means that these atoms are all flat and they're all about 120 degrees apart. Now notice that varies a little bit when you have different sized materials. Notice that this carbon is bigger than this hydrogen. So that's stretching that angle out just a little bit, okay? And that stretch gets even more pronounced when the group gets bigger. When we add a methyl group here instead of a hydrogen, it actually stretches it out even more to 124. But it's still close to that idealized 120 degrees we're expecting for a trigonal planar molecule. The other important part is that notice we have 2 bonds in between here. We cannot rotate that bond. It does not rotate. It is fixed in space. And that's why we had to have that cis-trans isomerization in our nomenclature. Okay. So why can't we rotate that? Well, we can't rotate that because if we look at where those unhybridized P's are, the unhybridized P's have to be in the same axis as each other to be able to overlap. And if they are started to tilt out of that same axis, they can't overlap. Therefore, you are breaking the pi bond. So they must be in line with each other. Because they have to be in line with each other, and it takes a lot of energy to break a bond, they are going to keep that orientation and not rotate. Okay. So if you did try to twist the molecule in half, it would break that pi bond, releasing lots of heat. And so we don't see this happen in regular atmospheric kind of reactions. You have to do something very, very troubling to it to make it break that bond. So most of the time, we're going to see those double bonds stay fixed in space. Okay. So because we don't have that, we have different possible isomers. And this is what we call our first stereoisomer. Stereo does not mean something that you play records on. Stereo means it is a fixed in space. So there's a spatial difference between the 2 compounds. So let's take a look at that and see how these 2 compounds are a little different here. So in this case right here, we have 2 methyl groups onto our alkene, and we know we can't twist that bond, which means those 2 alkyl groups are going to stay in that position. You can get a whole bottle of just them in that position, and they will never move. They will always be on that same side. And by the way, by same side, I mean, if we draw a line through our double bond here, those 2 methyl groups are both on that same side of that axis of that double bond right here. So that's that same side configuration. However, if we were to have synthesized the molecule such that when we draw the axis through this, when we draw the axis through this double bond, right here. Now notice this methyl group is on the opposite side of this methyl group, okay? And it's fixed in space because there's no rotation around that double bond. So that means we have to have a name to differentiate between the two different concepts. And when the two things are on the same side of the axis of the double bond, we call that cis. Cis meaning same, okay? And when they are on opposite sides of that, it is trans, meaning opposite, okay? So all double bonds with two substituents on them are either cis or trans, okay? Why do we care? Well, because they are fixed in space that way, they actually have different properties. So we have to be very careful when we name them. Notice that this cis-2-butene has a melting point of -139 and a boiling point of 4 degrees C. Well, that's different than the trans, which is -106 and a boiling point of 1 degree C. So they are different chemical compounds, and we must identify them as such. So that's why we have the cis-trans geometry of our double bonds. Any questions on cis and trans? Now that only works with two groups hanging off your double bond. Okay. Now, the alkyne is very similar. Oh, come on. There we go. The alkyne is very similar to the alkene, except for it is sp hybridized, meaning it has two unhybridized p orbitals. So what that means is that we have a p orbital that's in the x-axis right here, and then we have another p orbital that's in this y-axis here. Okay, and that z-axis that runs through the middle here, that's where our sigma bond is. Our first pi bond is above and below on this x-axis. And our second bond is to the side and to the other is our second bond. So that's how we get 3 bonds between 2 atoms, okay? We have a sigma bond that's directly bond between the two. We have one p bond in one axis over that bond, and the other pi bond in the other axis over that sigma bond. So that's the differentiation between that. And because we have this, we also have that linear molecular orientation. Okay, we're not going to do it again. All right, so let's talk about naming things, okay? So in the alkanes, all we cared about was the fact that they had no double bonds in them, and we had the AE, so like hexane, butane, it had AE in the name, so we'd have butane. This AE means we had a saturated hydrocarbon, no double bonds at all. If there's a single double bond in that entire molecule, you have to get rid of that AE and add an EN, okay? And the reason is it goes from an alkane to an alkene. So you have to have the "ene" in the word. So the way we do it is we number the parent chain and give the first carbon of the double bond the lowest number. The other important thing is both carbons of the double bond have to be in the parent chain. So that's the only difference from all the alkane rules we learned, except that you have to have both carbons from the double bond in the main chain, and it has to have the carbon in the double bond has to provide the lowest number. For a cycloalkene, we just put the number of atoms in the ring, and then with the 2 carbons of the double bond. And one of those 2 carbons is the 1 and 1 is the 2. Unless you have a substituent, then you can figure it out. But though you always start on that double bond in a ring. Okay, so let's do some examples here. So if we look at this compound here, and I've drawn it 2 ways. This is the stick figure. This is the most common way we're going to see it. But I also have the expanded version here, so you can like remember that there's hydrogens everywhere, that there's not a, that the hydrogens are understood. And in the case of this, we have a total of 6 carbons. So we have hex as our prefix. We have an alkene, so we have an EN in there. And we have no other functional groups, so we have an E at the end. Okay, so that turns this into 1 because our carbon starts on that one carbon, one hexene, okay? So if we have substituents, again, we number from the alkene first. So even if the substituent's a lower number, like the alkenes in the middle, we're gonna number from the alkene first. So we have the 1 here, giving us our substituent only on the 4, which gives us 4-methyl dash 1 dash hexene, okay? Notice we're locating where that double bond is every time. It makes it a lot clearer when we say that. If you just said hexene, people would assume it's 1 hexene, but it wouldn't necessarily be 1 hexene. So always put the 1 there if in and out. Okay, so now let's look at this one. Okay, this is the rule where you have to put both of the carbons on the double bond in the longest chain, because we actually have a longer chain if we follow these right here, but only 1 carbon of the double bond would be in that. So we cannot choose that longer method. We have to choose the one that has both of them in there. So that changes it such that, actually, let's see, it has to go this way, and then this way, and then there's 2 carbons this way, so that's gonna be our longest chain, giving us 5 carbons in our parent chain. So we have 1 pentene, okay? Now we put our substituents. We have an ethyl group on the 2, a methyl group on the 3, alphabetize that, 2 dash ethyl dash 3 methyl dash 1 dash pentene. Again, the double bond is the EN right here. All right, is this starting to make a little sense? Let's add, go ahead.
So on the second example, why is the methyl named first?
The methyl is the only substituent. So this is our only substituent here. And so our substituent goes before our parent. Our hexene is our parent compound. The 1 here just tells us where the double bond is. Okay, does that make sense?
Yes, and then on this last example, there was a question on the homework where it had a diagram like this, and like it started like at the bottom as the parent chain. Like how do you tell what the parent chain is like exactly?
Okay, the first thing you do is you highlight both of the carbons in the double bond, and then you find the longest chain from that, because both of those carbons have to be in your main chain. So if you start where even if you're going to have to renumber it something else, always start with the 2 carbons in the main chain and then find the longest branch from there. Okay?
Thank you.
All right. Okay. So, and again, we're following all those other nomenclature rules for alkanes. You know, we haven't changed anything. All we've done is change that EN for the double bond. Now for the triple bond, we have to use a YN. Okay. So the YN indicates we have a triple bond. And so we call that an alkyne. Okay. So in this case here, we use that same rule. You put the triple bond in the longest parent chain, both carbons of the triple bond, and then you find the longest chain from that, and that becomes your parent. So here we have 4 carbons right here. So that tells us butine. So it was going to be butane if it was a hydrocarbon. It was going to be butene if it was an alkene, but now it's butine because it has the triple bond. So single bond, double bond, triple bond, okay? We see how that, just that infix changes as we go through the system. Now we locate, again, trying to make our alkyne have the lowest number, and we locate it. So that gives us our 1 butine, and our only substituent here is our 3 methyl, okay? Now let's do this one right here. In this one right here, we have to give our alkyne the lowest possible number. So that's going to control where our substituents are, okay? So I'm going to go ahead and in yellow, I'm going to try to go from the other side and see if we can't trick it. So we're going to go from 1, 2, 3, 4. So that would put our alkyne at a 4, okay? So if I go from the other side with blue, we have 1, 2, 3. So this means from this side over, our alkyne begins on a 3. So that's why, because you have to have your alkyne or alkene start on the lowest number possible, we have to number from this blue side, this side over here. So that being said, our numbers are now like this. So we go 1 through 7, and it looks like we have 2 groups on that 6 carbon, okay? And they're both methyl groups. So let's build it up. We have an alkyne, but it starts on 3. So we have to go 3 heptyne, because we have 7 carbons, that's hep. And it was an alkyne, so we have yne at the end here. And we have 2 substituents, both on the 6. So we have 6, 6 dash dimethyl 3 heptyne, okay? So the only rules we added here are we changed the infix, the E, the YN or the EN, and we have to have both carbons of that and their lowest position. So that actually takes some ambiguity out of which side you start the chain on. Start it on the where the closest end to the double or triple bond is, and that makes it unambiguous about where to put your substituents. Okay.
I have another question.
Yes.
So like it's dimethyl because it's two methyl groups from the same carbon, but like
no, it's dimethyl because we have 2 of the same substituents.
Okay.
So they could be on different carbons, but we have 2, you could have 2, 3, or 4 of the same substituents, and you get to use those prefixes of di, tri, and tetra.
Okay. And there's 2 of them, so it's 6, 6.
And they're both located on that 6 carbon. So it's 6, 6 dash.
Okay.
Okay. And the di is for the fact that we have 2 of the equal groups. And so we have dimethyl because of that, and we have to locate all of our substituents. And they just happen to be on the same carbon. But if you put 6 dimethyl, it's like, where's the other methyl? You didn't identify it. So we have to go 6 for one of the methyls, 6 for the second methyl, and then 3 for the location of the alkyne. Okay? All right. So let's do a little bit more nomenclature here. Now, because these are used so extensively in the petrochemical industry, they actually have common names associated with them, which are actually the ones you're probably going to hear more often. So I'm going to give you the IUPAC name, the chemical name of it, and then the common name as well. So if we look at this one right here, we have 2 carbons. So 2 carbons is F. So we have an alkene, we have a double bond. So that turns it into from ethane to ethene. So this is the EN saying we have a double bond. But the common name is ethylene, okay? So it's like it's a substituent with a double bond. So the common name is similar, but not the same. The IUPAC name is ethene. The common name is ethylene. And you may know that from, polyethylene is a type of plastic made from ethylene. When you add another carbon here, you end up with propene, okay? 1, 2, 3, propene. But the common name is propylene, okay? The engineers like to add that YL in there to make it more fun, I guess. And in this case here, we've added a methyl group to our propene right here. So we have to locate our methyl group. And so we're going to number from the lowest double bond carbon first, which puts that methyl group on the 2 position. So it's 2-methylpropene. But the common name for that is isobutylene. And let me show you, if we draw this out right here, that's starting to look a little bit like an isopropyl group. And so its common name is isobutylene because it has 1, 2, 3, 4 carbons. So that's bute, but it's in that isopropyl shape, that propeller shape. So it's called isobutylene. Okay. Questions on those common names? It's good to have. Those are the ones you're going to hear a lot out in the real world. But the IUPAC name is always, of course, the most appropriate name. All right, so let's go with the alkynes. In the alkynes, we have that same rule that we showed before. And so the only difference is the YNE. And all those other rules apply. The lowest number in a chain, if possible, both carbons of the alkyne have to be in that main chain. Okay. Now, in alkenes, we showed that if you had two different groups on there, you have that cis-trans configuration, okay? So we have to show that in our system where we have our double bond somewhere in the middle of the ring. So in this case here, we have 1, 2, 3, 4, 5, 6 carbons in our parent chain. So that gives us hexene, okay? And so if we numbered it this way, it'd be 1, 2, 3. If we numbered it this way, it'd be 1, 2, 3. So our lowest number for the alkene carbon is 3. So we have 3 hexene. And if we drew a line through the double bond, right here, this axis of the double bond, one group is going to be on the opposite side of that axis as the other group, which gives us that trans configuration. Notice that it's italicized. When it's typed out, it's italicized. When you're writing it, you really can't tell. But the two groups opposite each other are giving us trans hexene. Notice those ethyl groups are not substituents. They are part of the parent chain. So,
A question.
yes.
So how is it 3 trans 3 hexane?
Okay. So do we understand the trans part?
Yes.
And we understand the hexene part. Okay.
Yes.
So if we number from this side 1, 2, 3, that first carbon of the alkene is on the 3 carbon. Okay. And just to double check, if we number it from the other side, 1, 2, 3, the first carbon on the alkene from this side is also 3. So that means our alkene is the lowest number possible is 3. That's where the
Gotcha.
3 hexene. Okay. And look, again, drawing a line through our double bond, we have one on one side and one on the other. That gives us our trans. So let's look at a different molecule. This one right here. This one gets a little more complicated. I'm going to redraw it as a stick figure so you can see it. Okay, so this is redrawn as a stick figure so we can find our longest chain. Okay, so we can start from either side of the molecule, but because we want to have that double bond on the lowest number, I'm going to say we start from this direction, go through here, go through there, and go through there. That gives us the longest continuous chain. We could have used this one too, but it would give us the same number. So that's going to give us our parent chain. And that's 1, 2, 3, 4, 5 carbons with a double bond in it. So that's where we get that's where we get the pentene right here. Because this is going to give us the shorter number, this is going to give us something like 3, this is going to give us 2. We're going to number from this direction. That's where the 2 comes from, 2 pentene, okay? And now, oh, there's another methyl group on here somewhere, right there. Sorry. Again, they would each give us the same thing. And now we have 2 substituents. And so if this was 2, this was 3, this is 4. Oh, I'm sorry, the methyl group's up there. I see where I went wrong. There is a methyl group right here. Right there, that's the methyl group I missed. Okay, so we have, this is our 3 and this is our 4. Okay, our 2 is here because the lowest number on that carbon. And so we're going to end up with 3,4 dimethyl right here, 2 pentene, okay? But now we have to determine cis or trans. And in this case, if we draw a line through here, right here, notice that both of the things that are in the parent chain are what we're looking at. So the parent chain is running in this direction here. They're both on the same side of both of those chains are on that same side. So we call it cis. Okay, so just, even though you have another group here, you have the parent chain is all on the same side of that axis. Would we name the one on the bottom? Did I answer the question in the chat? So, no. What would we name the one on the bottom right one? which is this one right here. So this one right here is the cis dash 3,4 dash dimethyl dash 2 dash pentene. We get the pentene from the 5-carbon chain. We get the 2 from the location of that first carbon in the double bond. We give the 3,4 because 1 methyl group's here and 1 methyl group's here. And the cis comes from the parent chain being on the same side of that double bond. Oh, I mean so this is actually, when we draw it out, one of the methyl groups becomes the parent chain and the second methyl group becomes a substituent. That's why I drew it out, because if you don't draw it out, you might be confused about where the methyl groups might be. So when I drew it out as the stick figure up here, it shows that this is the first methyl group right here. This is the second methyl group, and this is actually the third methyl group. However, one of those methyls actually contributed to the parent chain, giving us only 2 methyl substituents. Did that answer your question? All right. I'm going to admit and continue. All right. So that one was kind of easy because we had the parent chain deciding out. However, if we have 3 or more, okay. So do the parentheses indicate that they split off 1 carbon rather than in, yes, in the condensed version, you can have these brackets saying that they're both attached to that. That's why I really like drawing out the line drawing. So there's, you know exactly where everything's attached. All right. So that, cis and trans work great if you only have 2 substituents. If you have 3, it starts to get a little cloudy. And if you have 4, you really don't know. So we have to come up with another way of identifying whether it's which configuration it is when you have more groups than that. And we call that the E and Z configuration. So E and Z actually come from German, and the Z stands for zusammen, which means together or same. And the E stands for entgegen, meaning opposite. So what we're looking for is the groups that we're going to identify as either higher priority or lower priority as to whether they're going to be on that same side of the axis of that double bond. Okay, so I want to use this word clearly. I want to say this is our axis of our double bond. And so we're looking at things that are on the same side or opposite sides of that axis. Okay, so if they're on the same sides, that's a Z. That's analogous to cis. But it's slightly different because we have more than just 2 groups on there. And the E is analogous to trans, but it's different because we have more than 2 groups on there. So now we have another way to remember that is Z is together or on the same side, okay? So Z is similar to cis in that way, okay? So that's a way to remember that. But now, what's priority? What are we going to do about that? Well, we have some rules for priority, okay? So the first rule of priority is you look at the atoms attached to that double bond on one side of it or the other, and you determine the atomic number of that atom, okay? Not the atomic mass, it's the atomic number. So the higher the atomic number, the higher the priority, okay? So if you have 4 different things on your, like a hydrogen, a methyl group, an oxygen, and a chlorine, it's easy to tell which of those has the highest priority because of the increasing atomic number. Let's say you have 2 things on there and they're both carbons, okay? So you can't assign priority just on that first attachment. We're gonna look to the next atom over. And so you look at the atomic number attached to that atom. And don't worry, we're gonna do a few together. And then the last rule is that if you have a double or triple bond to another atom, you get to count that atom twice in determining priority, okay? So that is how we assign priority on the system. So let's look at that again, okay? So I want to do these assigning priorities, and we're going to do it stepwise to make sure we follow all 3 rules in the system, okay? So I'm going to blow this one up. So the first thing we need to do is we need to draw our axis down the down the double bonds, okay? So this is going to tell us the difference between cis and trans, okay? But to assign priority, we actually cut the molecule in half. So we're going to assign priority to one of the carbons of the double bond, and we're going to assign priority to the other carbon of the double bond. Actually, let me just call them A and B, okay? So what we do for that is we assign the priority on the A carbon first, and then we're going to assign priority on the B carbon, okay? So what's the first rule? Okay, the first rule is atomic number. So if we look at this right here, our atomic number for carbon is 6 here, 6 here, 6 here, 6 here. That didn't help us. We could not use rule 1 to definitively assign the priority on either side of this double bond. Okay. So we have to use the rule number 2. Go out from there. What is the differentiation? So if we look out from here, this is hydrogen. So that's atomic number 1. This is chlorine, which is atomic number 17. Right here. Anyway, it's higher than 1, okay? Which means this is the high priority side of this alkene. That's the high priority part on here. So I'm going to circle that as our high priority right here. And now, and actually I'm going to do it in red because it's the high priority for our red side of the thing. So now let's look at the other side, okay? If we look at the blue side, we have a hydrogen here and we have a carbon, okay? Carbon is 6, hydrogen's 1, giving this the higher priority group on this side, okay? So we've assigned our highest priority on each side of the molecule, A and B. Now, let's go back to that axis, okay? If we look at our axis going through both double bonds, are the priority groups on the same side or are they on opposite sides? Okay. Now, because they're on opposite sides, that's going to make this the E configuration in Gagan. Okay. So we have to make sure that we're following the procedure of looking at different parts of that double bond at the right times. Okay, let's do another one. We want to make sure we get this down. Okay. So again, we're going to draw this axis right here. And so we're going to look for the highest priority groups to be on either side. And now we're going to assign priority to the A carbon first. So we're going to look to just this side. We have chlorine and we have bromine. Bromine is higher atomic number. I don't know its exact atomic number. I think it's maybe 35. So that means that on the blue side, this is our highest priority group. And so now let's go look on the other side here. On the other side here, we have a carbon, which is 6, and then we have that understood hydrogen, which is 1. So on this side, our highest priority is this carbon, okay? So now let's look at that axis and see whether those two highest priorities are on the same or opposite sides. So if we're looking at our axis here, both our priority groups are on the same side of that axis, which means this is a Z. This was an E. Okay, so you have to look at the molecule exactly looking at where the axis is and then which side, which of the carbons has which substituent as the highest priority. All right, we're going to do a couple more. We're going to do 2 more just to make sure. All right, here we might have to use that second rule a little bit here. So the first thing we're going to do is we're going to draw our axis here. That's our double bond. And this is our A side, and this is our B side right here. And because that's, we're going to cut the molecule here. Now, looking at this real quickly, we can say, oh, we have a carbon, carbon, so that's the same, but there's another carbon attached to this side. So we can quickly identify that this is our higher priority side. Okay, so now let's look at the other side, our B side here. Our B side here has a carbon, and a carbon, and then this only has 3 hydrogens on it. This has 2 carbons on it, making this the higher priority side of our system. And now let's look at our axis. They are on opposite sides of our axis here, meaning that they are what?
E.
E, correct. They are engaging. Okay. So you see the process here. You have to make sure that things are on the same or opposite sides of the axis created by the two carbons of the double bond, but you have to assign priority to the groups on each carbon first. Okay. So let's do one more. Ooh, this is going to be fun.
I have a question on the last one.
Yes.
How did you know that there were 3 hydrogens on there?
Okay. In line drawings, if it's not specifically labeled something else, you assume that all the other bonds to make 4 bonds are hydrogens.
Oh, okay. Okay, thank you.
Yeah. No, that's a subtlety in line drawings. You got to remember. Side B again. Can I go over side B again? Okay. So E correlates to a trans-like configuration. Z correlates to a cis-type configuration. But because we have more than 2 groups, these are more precise. Okay. So in the B side here, if we look at what we have here, we have a carbon with 3 hydrogens on it, and then we have a carbon with 2 carbons on it. So the carbons are higher in atomic number than the hydrogens here, giving it priority. Okay. Okay. All right, let's do one more. And again, the first thing we're going to do is we're going to draw that axis right here. We're going to identify our A side and our B side. Actually, let me use different colors here. B. And on our A side, we have an understood hydrogen and a carbon. So that identifies us right away as having this is our higher priority side on the A. Okay. So let's move on to the B side here. So we have a carbon right here, and it's bonded to one other carbon. It's auto-correcting on me. One other carbon. Now we have a carbon here, but it's bonded to 2 other carbons. Okay, so we're done. We have differentiation. You don't have to go all the way around the ring. You don't have to come up with any other thing. The other thing you might want to imagine is the fact that there's one hydrogen here and 2 hydrogens here, just to make sure you have all 4 bonds to your carbon. That still doesn't change the fact that this group is now our highest priority. So if we assign that as our highest priority for the B carbon, let's look at that axis again. Our axis tells us that we have one group on one side of the axis, one group on the other side of the axis. So we have our Engagen configuration or our E configuration. Okay, do we see all the steps in it and can we use them properly? That's important for naming these structures correctly. Okay, so E is kind of like trans, but it's more than 2 substituents. Z is kind of like cis, but more than 2 substituents. And don't forget, it's atomic number, not atomic mass. Okay.
A question.
Yes.
How do you determine the axis?
Okay. When you draw the axis, draw a line through both carbons of the double bond.
Okay, thank you.
Okay. The third rule we didn't actually use, but let me go ahead and draw one right here real quick to show you what I mean by third rule. Let's say we had this compound right here. Okay, so when we, and there we go. Let's do this compound. So if we did this A side, we know right away our bromine here. But now let's do the B side here. Okay, so we have a carbon and a carbon. And this carbon actually, because we have 1 hydrogen on it, this counts, this first double bond counts as a carbon, but that second bond counts as a carbon. So that's the third rule, is not an oxygen. It auto-corrected on me, carbon. So the third rule is if, let's say we had a single bond to a number of carbon here, the fact that this double bond you get to count the carbon twice. You get to count the carbon for the sigma bond and the carbon for the pi bond. That's the third rule. And I should put one of those examples in here. Thank you. All right. Now, in the case of rings, you can get some isomerization. However, you cannot get cis-trans isomerization in rings until octane or above, cyclooctane or above, sorry, cyclooctene or above. The reason is there's too much ring strain. You can't actually get a configuration out of it. So everything from your cyclopropene down here to the cyclobutene right here, there's no way to get a trans configuration. You're always going to get that cis configuration. However, once you have an extra couple methylenes, extra couple CH2s in there, you can get it. And it can, notice this is the trans one. It's kind of folding in on itself. And this is the cis one. It's looking like the other cycloalkanes. Okay. So if you have larger than a cyclooctene, you might have to assign cis and trans. All right. So an alkene and an alkyne are things with at least one in there. Okay. But what if you have more than one double bond in there? Okay. Well, you need to consider the fact that you have not just an alkene, but now if you have two of them, you have a diene. If you have three of them, you have a triene. If you have four of them, you have a tetraene. Okay. And being that you have a diene, you have to identify the first carbon in each of those double bonds. And if there are two substituents on those, you have to identify the isomerization. Okay. So let's take these two examples here. We have a total of 7 carbons. So that's where we get our hepta from. Okay. And we have 2 alkenes right here. If we number it from this side here, we'd have 1, 2, 3. Our first double bond carbon would be on the 3. So we're not going to number it from that side, because if we number it from the other side, our first double bond carbon is on the number 2. Okay. So now we have our first 2 coming this way, carbons of our alkenes on carbon number 2 and carbon number 4. That gives us our 2 dash 2 comma 4 dash hepta diene. The di is just showing you have 2 alkenes, right? So now we have to identify our cis and trans, okay? So to do that, we just draw our axis here. The 2 groups are opposite each other. So the 2 is trans. And if we draw our axis on the second double bond, our 4 is also trans. So we're going to have trans, comma, trans, dash, 2, comma, 4, dash, hepta diene. Now, what if we change the isomerization around this number 4 here? That would look something like this, okay? So our 2, which is the first one here, is still in that trans configuration. But if we draw our axis on the 4, 5 through that double bond there, they actually are both on the same side. So that's where this comma cis comes from. So the trans is associated with the double bond starting on carbon 2. The cis is associated with the double bond starting on number 4. But we still have the same 7 carbons. It's still a di, and it still has double bonds, so diene. Okay. Now,
so if you have E or Z, where does that fit into the name of it?
Okay. Oh, great point. So the cis trans come at the beginning of the name. When we name E and Z, it also comes at the beginning of the name. So let's go back and name one of these right here. That is a good point. I did not say that. Okay. So this right here is going to be a chloro, and let's see, we're going to do 1, 2, 3, 4, 1, 2, 3, 4, 5. So that's going to be a pentene, okay? And the reason I'm going to start numbering here, 1, 2, 3, 4, 5, is that it gives our first substituent on the lowest number, and it gives our double bond on the lowest number. Okay, so see if I started from here, with number 1, our first substituent would be on a number 2. If I started back here, our alkene would be on a number 3. So I have to start from this side. So that's starting with that as a number 1. So our compound name is going to be, let's see, they're opposite each other. So that's Engagen, E dash 1 dash chloro, for having this chloro on there. 2, 3, comma 3, dimethyl, pent, dash 2, ene. Okay, so the designator of cis and trans or E and Z goes at the beginning of the name. If you have more than one double bond, you assign the first one first, the second one second, and the third one third, that correlate to where the alkenes are located. Okay? All right. So let's see. So the cool thing is that if you synthesize the molecule such that it has all cis isomers, it's going to look very different than if it had all trans isomers. So if we had all cis isomers in this compound, it would look like that. So this is all trans, this is all cis, and they have different physical configurations. Okay. So let's talk about how that's useful here, okay? So in the compound vitamin A, there is a all trans configuration except for in this ring here, which has a cis configuration. So notice all of the double bonds are in this trans configuration associated with that. And it's actually used by our body to oxidize this alcohol down to an aldehyde to be able to use it in the body. Okay. But if any of these bonds here were in the cis configuration, they would not work with the enzyme. It would not be able to be processed by the body. Okay. So you wouldn't need to put cis or trans in the name if you put E or Z. Correct. You use cis or trans or E or Z, not both. Okay. All right. So let's talk about the physical properties of these. So alkanes, you know, they were nonpolar compounds. They were less dense than water. Okay. They only have those dispersion forces. Okay. Alkenes and alkynes are similar to that, except they tend to have a slightly higher density. So they're just barely less dense than water, but they're a little more dense than the alkanes. They tend to dissolve in each other because of that van der Waals forces, those low dispersion forces, but they tend to be insoluble in water because they don't have anything to hydrogen bond to. Okay. So the other weird property about this is once we make a triple bond on a carbon there, if it has a remaining hydrogen on it, that is the most acidic hydrogen of any hydrocarbon. Okay, so what that means is it has a pKa of 25, which is a weaker acid than an alcohol, but a stronger acid than an alkane, and it can be deprotonated. When you deprotonate it, take a hydrogen off, deprotonate, you create this acetylene ion. Okay, and this acetylene ion is really cool because now you have these electrons available to go out and make a new sigma bond. Remember, when we have our Lewis base, it has electrons available to reach out and make a new sigma bond. So this becomes our good Lewis base and can go out and make new carbon-carbon bonds. Okay. So the acidity of that alkynyl hydrogen is the most acidic of the hydrocarbons. Okay. So what that means is that you can't actually make the acetylene ion in the presence of water, because water is the stronger acid, okay? And we do that, remember, we compare the acid strength for the one side to the conjugate acid side. And in this case, we have 25. In this case, we have 15. And 15 is lower than 25, making it a stronger acid, which means you aren't going to form very much of this at all using a different base like this, because the acid you formed is stronger than the acid you started with. So that alkynyl hydrogen is nice, but you cannot use it in the presence of water or other things like that. Okay, so let's talk about where it lands on the acidity scale. So we can't make the acetylide ion in water because the conjugate acid water is too acidic, okay? But we can make it in the presence of other things. So if we take water out of the equation, we can make this acetylide ion here, but we have to use a much stronger base to pull it off an alkene. An alkene is like is in between an alkane and an alkyne. That hybridization helps to make it more acidic. However, it's not as stable as the alkyne. And when we go down to that sp3 hybridized alkane, those are the least acidic compounds we probably are going to be dealing with. Okay, so we have those very high pKa's, making them very weak acids. But in contrast, when we do form them, they're going to be really, really strong bases. All right, so let's talk about identifying the different carbon bonds we have. So in the case over here, we actually have two substituents on there, but they're exactly the same, okay? Now we have three substituents here, so we would want to say, oh, is it EZ or cis and trans? But because they're exactly the same, it's neither. It's not cis and trans, it is not E and Z, because if that, because these are equal, we don't have any way to prioritize over either one. However, on the other side of the molecule, we do have prioritization available to us. And over here, this is obviously the highest priority group over here because we have a hydrogen here. And we have a carbon, carbon, we have an oxygen, carbon. Oxygen's higher in atomic number, which makes this our highest priority group. So what does that mean about this particular double bond in our compound here? Is it E or Z?
E.
E. I agree with you, because E means that it's opposite, and the Z would be the same, and those two higher priority groups on the opposite sides of that axis of the double bond. Okay.
I have a question about that real quick.
Yes.
Sorry. So that whole molecule, did you kind of divide it up into two parts?
Well, we were looking at the cis-trans isomerization, and only the double bonds have cis-trans isomerization. So I only identified the double bonds and worked with those first.
So on the other side, when you said that they, they're both the same, well, why didn't you keep going to that double bonded oxygen?
Okay, well, because the differentiation, we didn't have to. We had a hydrogen here and a carbon here. So this would have been the higher priority side on this one. However, there's no way to differentiate between these two. They're both CH3s. So neither one has a higher priority than the other. We can't assign cis and trans. We can't assign E or Z.
Okay.
Okay, does that make sense? Yeah,
yes.
So you have to have a differentiation between them to be able to assign that. And when we don't have it, we actually don't have the stereoisomer. That there is no isomerization possible.
So if one of them was an ethyl, that would have the higher priority.
Yeah, you add one more carbon to either one of those and it becomes the highest priority one. Exactly right.
Okay.
Okay. All right, so what we're going to look at is try to figure out how many cis or trans isomers are possible with this structural formula. Oh, okay. They don't give you the structure of pyrethrin. That's, oh, I should have. Okay, sorry, we can't do that one. I don't have that. But you might want to go look this up. It's actually in the book. The structure of the pyrethrin is in the book, and you can see that how many different possible cis-trans isomerization. The cool thing is the flour only makes one of those. And so that's the specificity of the enzyme systems we'll talk about later in a different chapter. Okay. So let's talk about that acidity of the alkyne again. Okay, why is that the most acidic one? And if we think about hybridization, if we have an sp3 hybridized, that means that we have an S spread out over 4 equal orbitals. And so we had one S spread out over 4 equal orbitals. That means it's about 25% of that S character, that spherical character. Okay. So the rest of them are that P character. Okay. So what that means is that it's located in a hybrid orbital that only has a little bit of S in it. If we go up to an alkene, we've taken that S orbital and spread it out over 3 equal orbitals, the sp2s, and then left that meaning our S character has gone up. It's about 33% of that spherical one. That spherical one can stabilize charge a little bit better because it's spherical, it's not dumbbell shaped. And then when we go to the alkyne, it's sp hybridized. We have 1 S over 2 equal orbitals, and that means it's half S character. It's more spherical than the other hybridized orbitals, therefore it can more easily balance charge. And that would help us understand why the alkynyl hydrogen is more acidic than the alkenyl hydrogen, which is more acidic than the alkane hydrogen, okay? So that's one explanation about how to keep those in track. And notice that we go from 50 to 33 to 25. So there's a bigger jump between the sp hybridized and the sp2 hybridized than the sp2 and the sp3. And you'll see that in the acidity if you go back to the table. Right here. You'll see there's a bigger jump between the alkyne and alkene than there is in the alkene and alkane. I think these are out of order. That's what's the problem here. All right, so that brings us to the end of the properties and nomenclature associated with alkenes and alkynes. Okay. All right. Questions on the nomenclature of alkenes and alkynes? Okay, well, for the last little bit here, we're going to talk about the reactions associated with and the reactivity associated with alkenes and alkynes. Okay, so again, with hydrocarbons, we just said they burn, okay? Alkenes and alkynes, we can do a lot more stuff with them because we have that really active pi bond that we can do things to it. We can add things to it. We can move things around. And so we want to look at that. So the first thing we want to do is we want to look at what we call the addition reactions to an alkene. Okay, addition reaction means we're going to add something across the alkene so that we're going to have something adding to the first carbon of the alkene and something adding to the second carbon of the alkene. And this can be symmetrical or unsymmetrical, and we can do it a bunch of different ways. So let's look at the first one here. The first simple one is what we call hydrohalogenation. And in this case, the hydro means hydrogen and halogen means halogen. So, hydrohalogen, think HCl, HBr, HI, hydrohalogenation. So how would that look? We would put a hydrogen on one side and we'd put a halogen on the other side. So in this case, our alkene becomes an alkane, okay? So in all these reactions, we're taking away the double bond by adding one thing to each carbon. Okay, the next thing I want to talk about is hydration. That's where we're going to add water across that double bond. And when we add water across the double bond, we get a hydrogen on one side and an OH on the other, generating a new functional group. Okay, so that's one of the good things about alkenes is you can use it as a root to many different functional groups. Okay, so the next thing is halogenation. So we're going to take our halogens, which are, bromine 2, iodine 2, fluorine 2, chlorine 2, and we're going to add them across that double bond. And when you do that, you get a halogen on each side. Okay, so we'll end up with what we call halogenation. And so you almost can call it dihalogenation. You get one bromine on one side, one bromine on the other side. And then the last one's a little trickier right here. This is called hydroboration. And we use that specifically because we want the boron to add a certain way across this double bond. So whenever you see the boron here, it actually changes where that hydrogen ends up going to. So we get the hydrogen on there, we get the boron in here. Most of the time, we actually take that boron off by oxidizing it, and I'll show you that reaction. And the last simplest thing we can do is just called hydrogenation. We can add 2 hydrogens across that double bond, turning it back to an alkane. So these are the different types of reactions we're going to be seeing in this chapter to start with first. Oops. And they are all called addition reactions. Okay. So before we can talk about the addition reactions and which side the things are going to go on there, we have to talk about the flow of energy in a reaction. Okay. So in the flow of energy in a reaction, we want to have a visualization of what's happening at each individual step in our reaction. And so what we have is what we call an energy diagram. So it's basically a visualization of telling us what's happening where in the reaction. So on the y-axis here, we have what's called the energy axis, and it's increasing. So that means this is a low energy side. So let's say it's not hot and it's not moving very much. And this is our high energy side. This is where you've stored a lot of energy or it's a lot of heat. Okay. And at some point, we're going to start with our starting materials here. And we're going to map that on the reaction coordinate axis, which is the x-axis. And so we're going to start always with the starting materials. And then we're going to go through some kind of change. Something has to happen to get that reaction to go. And we usually call that the transition state, whatever energy is required to make this reaction happen. And we have an energy associated with that. And then once it happens, it can go down from that. And the products can be have less energy than the starting materials, or they can have more energy than the starting materials. And that's going to tell us something else. So the components here are this curve where we start in energy, where we have to rise in energy to make the reaction happen, and where we come down and what do the products look like. Okay. So let's go that in a little more detail. Okay. The first thing we want to do is we want to identify that transition state. The transition state is this instantaneous part where bonds are making and bonds are breaking all at the same time. And because of that, it's very unstable and it's the maximum energy you form during the course of the reaction, okay? So it's always the top of the energy diagram. So if we look at the energy diagram, our transition state here is at the top here. So we had to put energy into the reaction to get to this where it will react, okay? And that is our next definition, activation energy. That's the energy we had to put into the reaction to make the reactants be at that energy, that transition state. So the activation energy is the energy that you had to put into the reaction to get it to that transition state, to get it to react. If you don't have enough energy to get the molecule over that, it doesn't go. It just stays the same. Okay. So that activation energy also controls how fast the reaction goes, or the rate of reaction. Now, the way it does that is, if the activation energy is really high, that means you have very few molecules have enough energy to reach that transition state, and it slows the reaction down. In contrast, if that activation energy is very low, that means a lot of the molecules can get to that amount of reaction, that amount of energy, and that the reaction goes faster. So when we look at our energy diagram, the height of this transition, this energy state, gives us an idea of this. So if we were comparing this reaction to a reaction that had an activation energy that was lower, this reaction with the lower activation energy would actually go faster, because you have more molecules obtaining this amount of energy to be able to go. So we have the transition state, which is the peak. We have the activation energy, which is the measure of the energy under that peak. And we know that the activation energy determines the rate of the reaction. So what else does it tell us? It also tells us the heat of reaction. The heat of the reaction is the difference in potential energy between the products and the reactants. Okay. Why is this important? Well, the heat of reaction tells us whether the reaction is exothermic, i.e. gives off heat as the reaction progresses, or the reaction is endothermic, it absorbs heat as you do the reaction. And the way we do that is we look at the energy of the starting materials and the energy of the products. So we have the energy of the starting materials right here on this energy diagram. And you're going to add energy, get to this transition state. You're going to break some bonds and form some new ones and come down to your products here. The difference between that starting materials and the products is your heat of reaction. In this case, our products are lower in energy. So that means this had more energy than this, so it gave off heat. So when our products are lower than our starting materials, we have an exothermic reaction. If instead we had our transition line come up and our products ended up here, but we had enough energy through the transition state, if our change in energy is positive, that means it's an endothermic reaction. If our diagram shows that our energy of our products is higher than the starting materials, it's an endothermic process. So the key things here are the transition state and activation energy, the heat of reaction, and that heat of reaction tells you whether it's exothermic or endothermic. So let's look at this one and see if we can identify everything that's happening here. Okay, so the first thing we want to do is look at this beginning of the reaction. We have our products here, our starting materials here, and we have our products here, okay? Our products are below our starting materials, which means we have an exothermic reaction, and we know that we're going to get to here. All right, wait a minute, there's more than one hump here, okay? Well, that brings us a new definition now. So we had to add a whole bunch of energy to get to this first transition state, and that's our active net energy of the first reaction that happens. But when it does, remember, this is a highly unstable, it is bond breaking and bond warring all at the same time. And then it comes down and makes some sort of kind of stable intermediate, okay? It's more stable than the transition state, but it's not as stable as the products. So this is what we call the intermediate, okay? So this is like when we break a bond to form something, but then it can react again with something else. When it does react with that something else, it comes up to a different transition state and probably a lower activation energy. And then it finally cascades down to products that we see here. So here we have a two-step reaction because we formed two different transition states. So that reaction happened in two steps. So one hump is a one-step reaction. Two humps is a two-step reaction, okay? And in two-step reactions, you always form an intermediate. And it's always in between those two transition states. And because it was this, so it's exothermic. So it's a two-step reaction. So if we had one that was like this right here, you have a one-step endothermic because this is higher and we only have one hump. So that's a great thing about the energy diagram. It teaches us how the reaction is progressing with this nice visual cue, okay? And so the two things we have on that two-step thing are the intermediate. So that's a high energy reactive material that is in between the two transition states. And The last thing I want to do is talk about the rate determining step. The rate determining step is the slowest step in the reaction. And the slowest step in the reaction is always the one with the highest energy barrier. So if your slow step is at the end, your highest energy area is at the end. If your slow step is at the beginning, your highest energy barrier is at the beginning. Okay, and we're right at 12:20. And so that's when I need to stop. So we will pick up on reaction mechanisms from here on Thursday. Okay, I'm going to go ahead and stop recording and let you ask questions while we finish here.